Greetings of the day. I'm Dr. K. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. The topic name is Plasma Beam Machining. Right. At the end of this session, student will be able to understand the basic working of plasma beam machining. This is the course learning outcome of the today's topic. Right. Basically, non-traditional machining process has three branches under which there are different machining process. The first one is mechanical, second one thermal, third one chemical and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Under chemical and electrochemical, chemical milling, photochemical milling, electrochemical milling. Under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Now we are in plasma beam machining. Right. Introduction to plasma beam machining. When the temperature of a gas is raised to about 2000 degrees centigrade, the gas molecules become dissociated into separate atoms. Okay. When the temperature of gas is raised to about 2000 degrees centigrade, the gas molecules become dissociated into separate atoms. Okay. At higher temperatures, 30,000 degrees centigrade, these atoms become ionized. Okay. Right. So at 30,000 degrees centigrade, the atoms become ionized. Okay. Right. The gas in this stage is termed plasma. Okay. So at 30,000 degrees centigrade, the gas molecules or atoms will convert into ionization. So that is said to be plasma. Machining by plasma was adopted in the early 1950s as an alternative method for oxy-gas flame cutting of the following materials: stainless steel, aluminium, other non-ferrous metals. Okay, so during 1950s only it has been started. Right. During that time, the process limitations regarding the low cutting speed, poor machinability quality, and the unreliable equipment were clear. Okay, so what are the limitations? Low cutting speed, poor machining quality. Okay, recently machining of both metallic and non-conductive materials has become much more attractive. Okay, right. An important feature of plasma beam machining is that it is the only fabricating method that works faster in stainless steel than it does in mild steel. Okay, so plasma beam machining works very faster in stainless steel than in mild steel. Right. Introduction to machining systems. In plasma machining, a continuous arc is generated between a hot tungsten cathode and the water-cooled copper anode. Okay, so here cathode and anode. A gas is introduced around the cathode and flows through the anode. Okay, the temperature in the narrow orifice around the cathode reaches 28,000 degrees centigrade, which is enough to operate a high temperature plasma arc. Okay, so here this content is very much important. At what temperature the plasma beam machining works. Okay, and here anode and cathode. So cathode material is tungsten, anode material is copper. These two are the important elements in this plasma beam machining system. Under these conditions, the metal being machined is very rapidly melted and vaporized. Okay, so here the phenomena of material removal is melting and vaporization. Okay, the stream of ionized gases flushes away the machining debris as a fine spray, creating flow lines on the machined surface. Okay, right. Plasma beam machining characteristics. The removal rates by this method are absolutely higher than those of conventional single point turning operation. Now let us look at these characteristics of plasma beam machining. So parameters and level. Velocity of plasma jet 500 ms miles per second. Material removal rate. Sorry, this is meters per second. 500 meters per second. Material removal rate 150 cubic centimeters per minute. Specific energy 100 watts by cubic centimeter minute. Power range 2 to 200 kilowatts. Voltage 30 to 250 volts. Current up to 600 amperes. Machining speed 0.1 to 7.5 meters per minute. Maximum plate thickness 200 millimeters. Okay, so here the removal rates by this method are substantially higher than those of conventional single point timing operation. Okay, right. Classification of plasma beam machining systems. Right. Plasma machining systems are divided into plasma arc, plasma jet, shielded plasma, air plasma. And let me reiterate. Plasma machining systems are divided into plasma arc, plasma jet, shielded plasma, air plasma. Okay, right. Now let us look at it. The figure 2. Transferred plasma arc system. Okay, so as shown in figure 2, the arc is struck from the rear electrode of plasma torch to the conductive workpiece, causing temperature as high as 33,000 degrees centigrade. Okay, now look at this figure. So here this is workpiece. Okay, this is electrode. Okay, this is nozzle and plasma gas is passing. Okay, and here HF coil is connected to the power supply, and This is arc circuit which is connected to the system and the workpiece. Okay, so here negative is connected to HF coil and positive is connected to arc circuit to the workpiece. Okay, right. The double arcing effect between the nozzle and the workpiece damages the electrode and the workpiece. Okay, so here what is the impact of double arcing? Double arcing effect between the nozzle and the workpiece damages the electrode and the workpiece. Okay, high heat transfer rates are found to occur during plasma arc due to the transfer of all the anode heat to the workpiece. Okay, so here high heat transfer rates are found to occur during plasma arc due to the transfer of all the anode heat to the workpiece. Right. Owing to the greater efficiency of plasma arc systems, they are often used for machining metals. Plasma arc does not depend on a chemical reaction between the gas and the work metal. Okay, plasma arc does not depend on a chemical reaction between the gas and the work metal because the temperature is high. The process is suitable for any electrically conductive material, including those that are resistant to oxy-fuel gas cutting. Okay, so here electrically conductive materials are best suited. Right. Now the second one is plasma jet. Okay, plasma or plasma jet. In this system shown in figure 3, the non-transferred arc operated within the torch itself. Okay, only ionized gas, that is plasma, is emitted as a jet causing temperature as high as 16,600 degrees centigrade. So here you can find the difference is that here we do not have this arc circuit which is connected to the workpiece and the setup as like plasma arc. Okay, so here that is eliminated. Okay, directly it is connected to the setup. Okay, that is the only difference. Okay, right. Since the torch itself is the anode, a large part of the anode heat is extracted by the cooling water and is not effectively used in the material removal process. Okay, non-conductive materials that are difficult to machine by conventional methods are often successfully tackled by the plasma jet system. Okay, since the torch itself is the anode, a large part of the anode heat is extracted by the cooling water and is not effectively used in the material removal process. Okay, non-conductive materials that are difficult to machine by conventional methods are often successfully tackled by plasma jet system. Okay, so usually non-conductive materials are very difficult to machine. Okay, next, shielded plasma. In this, gas shielded plasma, water shielded plasma are of two types. Okay, right. Now let us discuss gas shielded plasma. When machining different materials such as aluminum, stainless steel, mild steel, assisting gases may have to be used in order to produce cuts of acceptable quality. In such a case, an outer shield of gas is added around the nozzle to reduce the effect of the atmosphere on the machining gas, usually nitrogen or argon. Okay, so when machine aluminum, stainless steel, and mild steel, we have to go with assist gases. Okay, right. The shielding gas depends on the metal being machined. Okay, the shielding gas depends on the metal being machined. Okay, so based on the metal itself, we have to choose the shielding gas. For stainless steel, aluminum, and other non-ferrous metals, hydrogen is often used as a shielding gas. Okay, for stainless steel, aluminum, and non-ferrous metals, we have to go with hydrogen as the shielding gas. Okay, CO2, carbon dioxide, is popular for ferrous and non-ferrous metals. Okay, so for ferrous and non-ferrous metals, we have to go with CO2, carbon dioxide. Okay, for mild steels, air or oxygen may be used. Okay, so for MS, we can go with free air or oxygen. Okay, but for stainless steel, hydrogen. Okay, for ferrous and non-ferrous metals, carbon dioxide. Okay, right. Water shielded plasma. Okay, in the figure 4, nitrogen is used for machining while the shielding gas is replaced by water. Okay, so water forms a radial jacket around the plasma torch. Okay, so let us go through the water shielded plasma figure here. So here anode workpiece, okay, and this is scrap side, this is user side, and this is plasma torch, this is water curtain circulated around the jacket, and the water supply, okay, and the plasma gas is passing through these nozzles. Okay, right. The cooling effect of water is reported to reduce the width of the cutting zone and improve the quality of cut. Okay, so here cooling of water is playing a predominant role in the quality of the machining. However, no improvement in both the cutting rate and the sequences of the cut has been reported by Magoff during 1988. So Magoff researched or investigated that there is no improvement in both the cutting rate and the sequences of the cutting has been reported by Magoff. Okay, right. Air plasma. Compressed air is used as the machining gas instead of nitrogen or argon. Okay, see here air is passing, that is plasma gas. Okay, so here hafnium copper electrode nozzle, this is plasma workpiece. So here compressed air, okay, is used as the machining gas instead of nitrogen or argon. In the air plasma, we are replacing the nitrogen or argon with the compressed air. That is the only difference. The rest of the things are same. When air is subjected to the high temperature of the electric arc, it breaks down into its constituent gases. Okay, since the oxygen in the resulting plasma is very reactive, especially with ferrous metals, machining rates are raised by 25%. So here, machining rates are raised by 25% because of the reaction. Okay, right. The main drawback of this method is the heavily oxidized surface, which is frequently obtained in case of stainless steel and aluminum. Because tungsten is reactive with oxygen, hafnium copper, HFCu, or HFZR, that is hafnium zirconium. Alloys also replace tungsten electrodes. So usually we use tungsten electrodes, but in order to overcome these things, that means reaction with oxygen, we are using HFCu, that is hafnium copper, and HFZR, that is hafnium zirconium. Okay, right. So oxides will damage the workpiece. Okay, so that instead of tungsten, we have to go with either hafnium copper or hafnium zirconium. However, life of these electrodes becomes shorter. Electrically conductive materials such as stainless steel and chrome nickel alloy, steels, aluminum, and copper can be machined by air plasma. Okay, right. Since air is used for machining and shielding purposes, the machining cost is about half that of gas or water shielded plasma. Okay, so 50% cost reduction. So obviously we can go with air. Okay, when a gas mixture of 80% nitrogen and 20% oxygen is used, the machining rate of mild steel is increased by about 25%. Okay, but this is somewhat expensive, but the machining rate will be improved in the mild steel. This is the research outcome reported by Makov. Okay, so with this, let me conclude. Okay, so these are the references. And thank you.
Like, share, and subscribe. Hit the bell icon for more updates.